Hi, everybody. Yeah, like Renee said, with this presentation, Bob, John, Esther, and I would like to give an overview of ongoing and future work on the viscoplastic, viscoelastic, and viscoelastoplastic rheologies in aspect. And please note that this is work done by many other people as well. So Cedric, Renee, Juliane, and Timo, to name a few. And what the four of us will discuss in this joint presentation are the current features and functionality that exists for tectonic modeling, so lithosphere deformation modeling in aspect, briefly the material model structure, the rheological equations of these different flow laws, some recent applications, awesome applications, and then the updates we are doing to the viscoelastoplastic rheology models, and other additional ongoing work on the rheology. So what functionality in terms of rheologies currently exists in aspect for lithospheric tectonic deformation? We have the materials that provide nonlinear viscous, viscoplastic, viscoelastic, and viscoelastoplast, so VEP deformation, as we also saw in yesterday's talks. Then accumulated strain can be used to weaken and heal some of the rheological parameters. We can use particles or compositional fields to track lithologies, but also properties like strain and stress. And there are multiple nonlinear solver schemes available to deal with the nonlinearities introduced by the rheologies. So Picard iterations, Newton iterations. And then there's extensive ongoing work to make the rheologies even more complicated. And all this work on the rheologies have made the material model plugins grow very big. So we've been working over the last few years to factor out some of their functionality into smaller rheology models that can be combined in different ways by the material models. So for example, the viscoplastic material model, I hope you can see my mouse, asks a composite rheology model for the viscosity, and then an equation of state for things like the density. But this composite rheology model itself has been separated into simple rheologies that deal with one flow law or one deformation element, so to say. So in the viscoplastic material model, we combine, as you can see, viscous creep, so dislocation creep, diffusion creep, Farangitakis creep, with plasticity and with elasticity. And the equations for these different deformation mechanisms are as follows. Viscous flow, such as dislocation creep, can be captured by this power law relationship between the stress and strain rate, and it's represented schematically by this dash plot. Viscoelasticity, with elasticity represented by a spring element, combines the viscous viscosity and the elastic viscosity. And this elastic viscosity is the shear modulus times the elastic time step. And then for a viscoelastoplastic rheology, we need to combine that with a plastic viscosity computed based on some yield stress, in this case, a pressure-dependent yield stress that can also have strain weakening. That's what the W indicates. And plasticity is represented by this slider over here. Now, the viscoelastoplastic rheology in aspect was first described and used by Dan Sandiford in his 2021 paper to look at oceanic detachment faults. And I just wanted to show like briefly three applications of the rheologies in aspect. So in this model, they extended young oceanic lithosphere, so youngest in the center, and we first see this brief period of symmetric necking, and then we have one large oceanic detachment fault forming. And as you can see here, after 1.5 million years, the mantle material that moves up along this fault is actually undergoing a solid block rotation. So everything red over here indicates a clockwise rotation. And the rest of the plate undergoes this rigid plate motion. So the area in between is a transitional zone between the solid block rotation and the rigid motion. And as you can see here from the strain rate, that means some compression in the top few kilometers, and then extension in this triangle below. And Dan coined this flexural process apparent unbending, because the change in the curvature is measurable by straightening this detachment fold, and apparent because the footwall wasn't bent in the first place. So it's a stress accumulating process ongoing here rather than a stress releasing process. Another example, this time of a viscoelastic deformation, is this example by Guaiza and Naliboff from last year. And they noticed like the segmentation of the margin of the Labrador Sea in based on the different domains. So there's this northern segment without any necking of the crust and mantle and without hyperextended crust, while in the south we see all the three different domains. And when they include, so on the left is their 3D model, when they include strength heterogeneity in the, so strength variation in the lower crust along strike of the rift, we can, they also see these different segments even early on in the rift history and later on. So when they compare the different margins, you can see that they find this very similar pattern. And as the last example application, there is this viscoplastic application by Farangitakis and co-workers, and they looked at the impact of either oblique inheritance, so oblique strength heterogeneity, or changes in the plate motion, in the extensional plate motion. So starting off initially with an oblique rift, transform rift configuration, oriented orthogonal to the extension direction east-west, and then changing the extension direction after 5 million years then leads to different behavior and life expectancy, basically, of the transform folds in between the spreading centers. So for small obliquity of the plate motions, the transform folds die out and they live longer for the higher obliquity plate motions. Now, when we were running models with the existing viscoelastoplastic implementation, in rift setups, like in the previous examples, we noticed some issues. And also when Esther is working on the rate and state friction implementation, we saw that the solution is very sensitive to the model parameters. So a slight change in the parameters can make a model fail, as Daniel also mentioned yesterday. And then some additional testing, for example, with this simple extension benchmark based on Kaus 2010, it's where we have a block of material and we extend it and we form these shear bands. We saw that in some places, the stress invariant can exceed the yield stress. So this is where everything that's not blue, this is where the stress is exceeding yield stress. And this is not something that should happen. So we then rederived the implementation of viscoelastoplasticity from Moresi et al. That was used for the ASPE implementation, and we found some inconsistencies. And these rederived equations, they actually matched with the updated expressions in Farrington et al. From the same Moresi research group. So I'll quickly go over the derivation of these equations. For linear elastic materials, the stress tau here is linear related to the strain. So 2 times G times the strain gives the stress. However, in ASPE, we write equations in terms of the effective viscosity that relates to stress tau here and the strain rate. So to fit this elastic relationship into this formulation, we take the time derivative. So the stress derivative and the strain derivative, that gives us the strain rate. So that gives us this formula where we include these two rotation terms. And then we approximate this stress derivative with a finite difference scheme, and that's this part. So the new stress minus the old stress divided by the elastic time step. And then when we rearrange this thing, we can get out the strain rate. And then we can rearrange it again to get these two terms, and one resembles a viscous term, like the viscous stress strain rate relationship, and the second term looks more like a force term, and this force term tau zero that only involves old, so stresses from the previous time step. So we have the old stress t, tau t, here and here, and this what is it? Tensor is based on the old velocity. Now, for the viscoelastoplastic formulation, we have to add this force term into the Stokes equation, this thing on the right-hand side. And then we have to find an expression for the effective viscosity. So we first assume no yielding, so viscoelasticity, and we compute the effective viscosity from the viscous viscosity and the elastic viscosity. And then we can compute the new stress based on this viscosity, the current strain rate, and the old stresses affected and rotated into the new time step. We can compare this current stress with the yield stress, tau yield, and if it exceeds it, we can rescale the viscosity such that the stress does not exceed the yield stress. So to get this current stress, we need to access the old stress and also access to some other solution variables. And in the current implementation, this total update to the stress, which is stored on the compositional fields, was done through the reaction terms. So once at the beginning of a time step during the advection solve. Now, however, we update the fields during the nonlinear solve through the reaction term. So we iterate also on the compositional solves. And we use the reaction terms only to update the rotation of the old stress with the current velocity fields, because we were using the wrong old stresses. And then to do the final update of the stress on the compositional fields, so not internally in the material model, but on the compositional fields, we use the operator splitting method at the beginning of the next time step. That's a bit counterintuitive, but it works. So maybe what's more important for you is to see how that changes, how that would change your input file. This is not merged into ASPE yet. This is all ongoing work. But the first thing would be to use an iterative advection scheme. So not only iterate on the Stokes equation, but also on the advection equations to include operator splitting, which is done through this line in the input file. To use discontinuous, so DG, compositional fields for the fields that store the stresses. To not use stress time averaging, no plastic dampers, no elastic dampers, and no fixed elastic time step, and assume that and set the elastic time step to equal the computational time step until we can justify a variable elastic time step. Now, all of this is in the PR 4370 for you to try out if you want. You can there also follow our discussions. And although I said that we turn off the dampers for now, this is the total scheme that we're working towards, where we have viscous creep, so diffusion, dislocation, Pyros creep in series with a damped viscoplastic element and a damped elastic element. And these dampers here, they should stabilize the solution, help to stabilize the solution. Now, we have also been benchmarking the new elasticity implementation. So we started off with some very simple benchmarks, so they are very simple graphs, but we initialized the compositional fields that represent the stress tensor elements with some values here, 20 megapascal, and then do nothing. Let's just let the stresses relax. And then we can see that the resulting stresses plot on the analytical solution. Similarly, when we start with zero stresses, but have stress build up through the boundary conditions, we also again follow the analytical solution. Now, if we go back to the brick extension benchmark, so where we extend this brick, we can now see that the resulting strain rate field is much less noisy. So the new ones on the bottom, we don't have this pattern outside the shear band. The shear bands are a bit wider. And more importantly, the stress is now limited to the yield stress. So we don't have any stresses exceeding the yield stress. And then there is, however, a new bottleneck at the moment for these new implementations. As we iterate over the advection equations as well, the number of solves, advection solves, is greatly increased. And you can see that from the little table I made down below, where I compare the old VEP implementation with a Picard solver, the new one with a Picard, and the new one with Newton. And you can see that the number of Stokes solves increased, but the number of advection solves increases much more. And then the wall time increases as well. And 77% of the wall time is now spent in advection assembly instead of solving the Stokes equations. However, we know what's the probable cause of this, and we know how to fix this. So this is hopefully just a temporary bottleneck. And what's also important, if you switch to the Newton solver, we drastically decrease the number of iterations. And on the right-hand side, I plot the nonlinear residual per nonlinear iteration. So every break in the lines is the beginning of a new time step. And then black is the old implementation, gray and blue are the new ones. And we can see that sometimes the residual or the convergence is better in the new implementation, sometimes it's worse. And if we use the Newton solver, then it's best. Then there is also a 3D benchmark that Esther performed, where we take a cube and we shear it for a time period of 0.5. And we continually rotate it. And that leads to a stress value for the XY component of the stress tensor that does this upper right graph. So it's sheared until 0.5. And then we zoom in onto this little square onto the right bottom graph. And there we can see in black the analytical solution, in blue the old implementation, in red the new implementation, and then for several different time steps. And we can see that with smaller time steps, we approximate analytical solution better, but also that the new implementation is closer to the analytical solution as the old one. And that's better shown in this graph on the left, where we plot the error with the analytical solution over time. And we can see that red stays like below 0.5% throughout the run. There is, however, this increase for the first 0.5 time, this quadratic increase, and we're still trying to figure out why that's there. It's not due to rotations, due to the shearing part of the implementation, and we're still trying to figure out why that's happening. So based on all of this, can we maybe make some recommendations already? Yes. Once we finish testing and understand where these small errors come from, once the updates are merged, then please use the new implementation. However, if you're already using viscoelasticity, we don't expect many changes because the current method gets very close to a wide range of analytical solutions, but it will be worth testing to see what the new implementation does. For viscoelastoplastic problems with a constant yield stress, the results may not differ so much either. But when you have localized shear bands, then there may be notable changes. So yeah, and any additional complications, I would wait with that until the new implementation is merged. We have also just started testing the new implementation with some complex models where we first rift and then compress lithosphere and astenosphere. And they show fairly poor convergence with the old implementation, and hopefully we can improve on this as well. Now, if you have any ideas for new benchmarks or you observe some odd behavior in your models, please get in touch with us. And then I'll finally say that we are also working on a paper that describes the new viscoelastoplast implementation. It's, however, foremost a comparison of using particles versus compositional fields for lithospheric deformation models. So we evaluate the accuracy and the costs of both methods for benchmarks with different rheologies for mesh deformation and free surface, and in an application of lithospheric inversion. And the wonderful thing is it's a joint effort of a lot of people in the community. This is where I hand over to John.
Great, thanks, Anne. And then can you just advance to the next slide?
I think so. Yes.
Great. So thanks, Anne, for that great summary. And I was just, oops, it looks like you signed out.
Yes. I moved my cursor. Am I back?
Yep, perfect.
Okay.
Yeah, so sort of to conclude the talk, and then Esther will be giving a summary of rate-safe friction at the end of the talk as well. We just want to talk about some of the additional ongoing work in aspect related to rheology, in addition to the viscoelastic plastic work that Anne just covered. So I'll start off with the things which are currently in progress. So one is the first one is associated plasticity. Oh no, it's fine. Actually, it's probably easier just to go to the next slide, actually. And so then the first one is associated plasticity. And so basically what associated plasticity does in most cases in our formulations, we assume basically that the dilation angle is 0. But then as a result of that, what ends up happening is the angle of the shear bands is resolution dependent. And so at low resolutions, you basically won't recover the theoretical more Coulomb angle of the shear bands until you get to brittle shear bands until you get to very high resolutions. But what you can do, and this is following a paper by Enson Choi and Kenny Pedersen in 2015, is that if you set the dilation angle equal to the friction angle, you can recover the correct shear band angle at basically any resolutions. And so this is work that was led by Cedric, Timo, and then I contributed a bit as well. And so then we've tested this. My recollection is that we basically, all of our benchmarks worked. And so then over the next few months, we're going to be working on implementing that into sort of the main branch of ASPE. And then there's a couple, oops, and it actually went to Slack. Sorry about that. But then we're also going to be working to test the, there's a couple different ways to do this, implement this. And so we're going to be testing the sort of the accuracy and of efficiency of an implicit versus an explicit method. And the implicit one involves actually doing compressible deformation, which is sort of an interesting next step as well. But then we'll also be testing this in combination with the plastic damper that Cedric led the implementation of, and then the new VEP rheology. Next slide. Great. And so then this is work that's being that was sort of led by Bob and Cedric and I helped a bit here as well. But the idea is that the best way to actually or a different way to actually perform mathematically having a composite rheology is to do it in an iterative way. So right now, what we currently do, if we have, say, diffusion and dislocation creep, viscoelasticity, Pyros creep, and then plasticity, is we harmonically average them, or at least we harmonically average the creep mechanisms for using all of them. The alternative approach is to actually do a local iterative scheme to actually decompose unique strain rates for each one of those individual mechanisms. So Bob has done a huge amount of work implementing simple test cases for this. This is in the code. What we're going to be doing probably this winter or maybe over the summer or at the hackathon is trying applying this to more complicated test cases. And we'll probably need to work out things like what type of local iterative scheme do we use? Right now, there's a new iterative scheme. We found that it's fairly slow in some cases or doesn't converge, so we might need to try a fixed point iteration. And we also need to adapt that scheme for elasticity. But then this is fairly far along, and we're hoping soon we can start testing it and applying it to very complex models. And next slide. All right. This is one, I think we've talked about this the last two aspect user meetings. I see Juliane laughing in the background. Bob made interesting comment when Ann and I talked about this. He said the hydrofracturing is like nuclear fusion. It's always 10 years away from being 10 years away. And that's what it sort of feels like with the hydrofracturing. But this year, I think we're actually close. So then this is work that Juliane, myself, and then Jonatha and Perry-Houts have been working on for a couple of years. And so then this is based on basically the approach outlined by Tobias Keller in a 2013 paper. And at this stage, what we have actually done is that we've implemented the physics of this. And so if you look at the plot on the left, in ASPEC, we can actually confirm that the physics works if you basically add an additional fluid pressure into the yielding mechanism. What we have not successfully done is gotten proper convergence for a time-dependent problem. And basically at this stage, what we need to do is there's all sorts of stabilization methods outlined in the Keller paper. And so over the next couple months or year, that'll be the task is to try and implement those and have hydrofracturing with basically reasonable convergence behavior. Because at the moment right now, it may break on the first few iterations. It's extremely nonlinear. But the hope is we can have that working sometime in the next year. All right, and then the next slide.
Let me try to get out of this presentation so that Esther can share.
All right, sounds good.
Okay. Oh yes, I got my mouse. Ooh, good.
All right, Esther, is the next one the rate state friction? Perfect. Esther, are you on mute?
Yeah, sorry. When I was sharing my screen, I couldn't unmute myself. But now I got it. So here we are. Yeah. So the next thing that we want to have in ASPEC, and what I have been working on the last 2 years, is to have rate and state friction in ASPEC, which is useful when you want to model seismic cycles and earthquakes. And I gave a presentation about that last year, but I'll just remind you, and probably not all of you were there last year anyway. So the rate and state friction equations is a set of two equations. So we have this one for the friction coefficient, and then we have another one for the state variable, which is called theta. So the friction coefficient, is made dependent on velocity. In our case, we don't use velocity, but we use strain rates as we are in a continuum. And then it says basically that when I have velocity jump, which is upwards here, and it goes from slow to fast, then my friction angle increases drastically and then slowly decreases again. And then when I have another velocity jump and it becomes slow, for example, then there's the direct effect and the friction angle becomes a lot smaller, and then it gradually increases again. So this is the rate and this is the friction coefficient equation. And this increase is dependent on the state variable theta here, which again depends on velocity. So this is quite a complex system when we have the friction coefficient depending on velocity and the velocity depending on the friction coefficient, and vice versa. But I have had a few good results so far, which I presented last year, where we have the velocity, the maximum velocity in the model, which stays constant for a couple of 100 years. And then we see this big peak, which is the earthquake, where we just jump up 7 orders of magnitude in the velocity. And then it goes down again. We have an interseismic period and another earthquake. And we can see the same here in a simple, the simplest drag slip model. And this is just the slip lines over time. And we see that here, there's not much slip happening. And then there's a period where we have a lot of slip at the same time. And this is something that I've tried to benchmark against an analytical solution by Lapusta, which many codes use to benchmark their rate and state friction implementation. And this is as far as I got until last year. And then this year I ran into some issues. My state variable turned negative and we had to find out why. We solved that problem. And then I found a bug in the current viscoelastoplastic formulation, which Anne mentioned, that the stress residual is not 0 when I'm in yielding. So this had me back a bit. And there's quite a lot of challenges left for rate and state friction. So we have this yield stress, which is not correct in the current VEP formulation, but which should be better in the new VEP formulation. For my rate and state friction seismic cycle models, as they go over many time scales and go to like milliseconds for time step sizes, they are very sensitive of all these elastic and plastic implementations, which is why they really didn't work for the old VEP, and which is why, well, which is a good part why we were working on the new VEP formulation. It's also that I have this condition for rate and state that I always need to be yielding, even if there's only a tiny bit of motion happening. And I mean, this is the part that didn't work in the old VEP. So right now I am testing the new viscoelastoplastic framework, also in the rate and state friction model, to see if the new formulation performs better. But I also had a lot of improvements this year in the rate and state friction, so maybe it's not that far anymore to be merged in ASPECT. And I know that many of you are looking forward to this functionality. So I fixed my bug with the state variable theta. I now get correct values when I use theta on particles. And before that didn't work when I used it on fields, because theta can be like 20 orders of magnitudes different from one field to the neighboring field. And if I use particles, there is no interpolation between them. And then I implemented the Lapusta time stepping scheme from that Lapusta paper that I talked about earlier. And that ensures that I can capture all the timescales that are relevant for the seismic cycle. So from very small, just before an earthquake and during an earthquake, and then also have bigger time steps in between. Then I also cleaned up the code and made a first pull request, which already includes the structure that I need for the rate and state friction implementation. And I also did some other changes, like I can now specify which materials should use rate and state friction. Before it had always to be a material called fault. Yeah, so there has been a lot of improvements, and I'm very happy that we have come quite far with the new viscoelastoplastic formulation. And that's it for this presentation. Yeah.
Excellent. Thank you so much.